Okay. While most of you are still struggling to install the package WGCNA, I would like to demonstrate one more thing. So now I correlated only one phenotype to my eigengenes, to one eigengene. I can use, by changing that trait's data frame, I can just correlate all the traits to one eigengene, and I will get a vector with the values. Or I can just correlate it, all eigengenes, to each other, and I will get a correlation trait matrix. Okay? So here, heading for the columns, I have all traits. And heading for the rows, I have all module eigengenes. And I can then identify within this matrix, I can print it as a heat map, the correlation coefficients to each other. And then I choose the highest correlation coefficient for a trait that I'm interested in, and I look at the module eigengene it correlates to. And then I have these variables, module colors, which is a vector that corresponds to the length of the number of genes that I have. This 3,600. So it gives me the affiliation of each gene to which module it belongs. Okay? Let's say I'm interested in color salmon. I want to identify all the genes of salmon. Genes salmon. I can say which module colors equals salmon. And then I will get a vector that is about 90, of length 90, corresponding to the indices of genes in my original data file, in my original gene expression data file. Okay? It's all in the PDF file that you have. I know that some of you are struggling to install the packages, but once you manage to install the package, you can just follow it. But even if you follow it, it will not help you if you don't understand the principle of WGCNA. And the principle is to first find modules of genes that belong together. Once you have your modules that belong together, you calculate your module eigengenes, so you get one row, one column vectors. So you get a vector for each instead of having a matrix for each. Once you have these module eigengenes, you correlate them to your traits of interest. By the correlation coefficient, you can then determine whether a trait is highly correlated, let's say greater than 0.5, that's a correlation coefficient, is highly correlated or negatively correlated to a module. Then I can go back to my original data, look which genes correspond to a specific module, extract this data, and look at the genes. I know it sounds a little bit abstract, but this is how it works. Okay? So the next step that what many people do, but I don't believe in it at all, and I wouldn't recommend you to do it, but I still have to mention it, is you do gene ontology term analysis, Go. That's why we installed the package go.db. Has anyone heard of gene ontology term analysis? Can anyone explain it? So in Go term analysis, what you do is mainly based in plants, is mainly based on Arabidopsis. So in Arabidopsis, all the genes that they exist, we have a pretty good idea what their functions are. So, and we sorted these genes according to their functions. Some have metabolic functions, some are hormonic functions, some control growth, and so on and so forth. So they are clustered together. Now we can impose our gene set onto these Go terms, and then we will know which Go terms are overrepresented in a specific module. So if you're looking at a phenotypic trait, and it tells you, yes, you have a Go term associated with growth, then you probably have a gene that controls growth in your module that you're looking at. If you have a small module, you can then manually look at each gene and you can blast it and try to figure out the exact function of it, so that you can report that, or you can go back to the lab and try to manipulate the gene. So that's one option. In many options, what will happen is, since we're working on plant data, plants have a lot of genes. So you will have modules of sizes of thousands of genes. Then it will become very difficult to identify single genes. So according to the method of WGCNA, you then sum up the correlation for each gene in your module, and the one that gives you the highest sum is the gene hub that will have the highest impact on the trait that you're looking at. But again, in my experience, it has never worked. Instead, what I did, I created an algorithm that can reduce the number of genes that you have in your module that have the highest impact on your trait. So let's say you have 1,000 genes in your module. With this algorithm, you can narrow it down to 40 or 50 genes. It's called the genetic algorithm. It uses the principles of evolution, and it's an optimization algorithm. But we won't go into this. Once it becomes available, you can just use it. So then, once you have only 40, 50 genes, you can inspect them manually again. It's much, much easier to look at 40, 50 genes rather than looking at 1,000, 1,500 genes. If this is what you want to do instead of Go term analysis, you can obviously do Go term analysis. There are lots of tools, web-based tools available, where you just paste in your list of genes and it gives you back your Go terms. For many people, that's enough. And this is also how I would like to conclude WGCNA. I'm sorry that it didn't work out as I hoped it would. But for the ones who managed to install, maybe you can finish the first 2 tutorials and we can try to help you. Who didn't manage to install WGCNA? Everyone installed WGCNA? Okay. No? Who still has problems installing? Raise your hand. One person. Awesome. ¿Qué haces? Me quedo aquí ahorita. can just use the PDFs, right? So originally, the plan was also to show you a tool where you can visualize networks. It's called Cytoscape. It's a graphical user interface tool where you can, I think in WDCNA there's actually a function where you convert, you can convert your network into data files that you can then import into Cytoscape, and then you can play around. You can drag and drop the nodes, you can delete edges, and so on and so forth. You can actually save the networks in high resolution. It's high resolution, so you can actually publish them if you wanted to. There are other packages, but Cytoscape was specifically developed for biological data. And if you're interested in the subject, there's actually a book by Steve Horvath on WGCNA. I think you can download it from his website. And you can look at it, look at the math, and then you can use the tutorials that you have here now. Try to understand it. If you finished it, you can go into the next tutorial. There are enough tutorials. Still, you have to change your name. I'm sorry. Yeah. Just get a new birth certificate, change the name. That's it. Yeah. This? But this is not a correlation. Okay. When I correlate all modules to all my traits, yeah, I get a correlation coefficient matrix. Okay? So I see that absolute fat value has a 0.37 correlation coefficient to my module 2. Yeah, module eigengene 2. Yeah, let's say, oh look here, I have a correlation of 0.6 of weight to my module eigengene 3. Yeah, let's say the module eigengene 3 represents module salmon, color salmon, right? I want to know which genes, which actual genes are in my module. Right now I don't know what the genes are. I just know that there's a high correlation between the weight to module eigengene, module 3, module salmon. So there is this variable called module colors, which is, if you look at the length of it, should be 3,600. Look. Module colors, right? Did you create it? Did you create it? Yeah, it's 3,600. And it contains, it's a vector of colors, right? Color names. Yeah? Okay, or yes. If I look at it, look. Pink, magenta, green, red, turquoise, gray, so on and so forth. No, it's not random. These are the indices of the genes in my original gene data set. when I make the correlate, when I build the hierarchical tree that you saw before, you know, this tree with the colors, it's still here, right? There are 3,600 genes here. Okay? They are not in the same order as in your original gene expression file. They are ordered according to how they cluster to each other. So they have a different order. Okay? But I want to know, let's say, I'm looking at salmon, where do these genes are located in my original expression file? So I will have this vector called color, what was it called? Module colors that will tell me the color of each gene, where it belongs to. Yeah? So I'm asking where in my vector, give me the indices of where I have the color salmon. And then, when I get this, it will give me numbers, okay? So, my first gene in my original gene expression data sits in column 32 that belongs to module salmon. The next gene sits in column 146. The next one in 172. All these genes that you have here belong to module salmon. And this is what you know. And now I can go back to my gene data and look at the actual gene names. And if I have the gene names, I can look up the functions of them. Yeah? Because this order doesn't represent the order that you have in your data matrix, in your gene expression matrix. Other color. You just look at the colors. I just took salmon. I could take pink, green, tan, black, turquoise. It depends what I'm looking at, what I'm interested in. What you have to keep in mind for this method is that, first of all, you're not throwing out any data. All the genes that you have in the original data set remain in your data set. When you do differential gene expression, your premise is that I will delete a few genes. Genes that are statistically insignificant. Here, you're basing your relationship between genes and phenotypic traits based on a linear relationship which is determined by your correlation coefficient. So even if you have very minor and subtle changes in the gene, these can still be highly correlated to the changes that you would find in your phenotypic trait. So this gene could be actually have an impact on your trait.